Welcome back to the Deep Dive, the place where we don't just swim in data, we dive down to the bedrock to extract the vital signals from the noise.
That's the goal.
And today, we are really opening the hood on the modern factory floor. We are focused on the highly technical, absolutely crucial challenge of making AI useful in industrial operations, specifically through predictive maintenance.
Yeah, and this is a deep dive into data strategy, not just data. We are moving way beyond the philosophical talks about automation and, getting to the raw mechanics of it.
Right.
How do you turn these impossibly high-dimensional, really noisy sensor streams, the kind of data you get from gearboxes, high-speed assembly lines, even wind turbines, into something you can actually use?
Into an accurate prediction.
Exactly, an accurate, usable prediction. And our sources today, they make it crystal clear. Success here isn't about just collecting the most data.
It's not about having the biggest data set.
No, it's about having the smartest data strategy.
That's the core tension we really need to unpack today.
Yeah.
The listener has given us sources that, they span everything from the high-level economic forecast for smart manufacturing.
Right.
All the way down to the specific mathematical techniques used to shrink a data set from, 64,000 columns down to just 2 or 3. It's a huge range.
And that really defines our mission for this deep dive. We're going to start by mapping out what you could call the evolutionary ladder of industrial maintenance.
Okay.
Put the economic incentives into context. Then, and this is where we'll spend most of our time, we're going to dissect a crucial real-world manufacturing case study.
The bottling plant.
The bottling plant, yes, to really expose the core technical bottlenecks. And finally, we'll reveal the essential technical shortcuts, the things that make this all work in practice.
So things like feature engineering and dimensionality reduction methods like PCA.
Exactly. The methods that can turn what looks like an impossible multi-year computational problem into one that, a simple AI can solve perfectly.
All right, so let's start high level. Predictive maintenance, or PDM, we hear this term all the time, but it's not just a piece of technology, is it? It's more like the highest point on an evolutionary ladder of asset management.
That's a perfect way to put it. And to really appreciate the leap that PDM represents, we have to understand the foundational levels, the older rungs on that ladder.
Okay, so where do we start? What's the bottom rung?
Well, if we look at this maintenance maturity model, we start at the very bottom with 2 classic levels. Level 1 is reactive maintenance.
The old run until it breaks method.
Exactly. It's the oldest, most expensive approach you can imagine. You run the machine, a component physically fails, everything stops unexpectedly, and then you scramble to fix it.
And the costs there are not just the replacement part.
Oh, not at all. You have the unplanned downtime, which can cost thousands per minute. You're paying for emergency labor, and often the failure of one part causes collateral damage to others. It's a disaster.
Okay, so that's the bottom. The first step up from that chaos was level 2, preventive maintenance.
Right. And this was a massive improvement. This whole approach is driven by calendars and checklists.
So like changing the oil in your car.
Precisely. You schedule maintenance tasks, oil changes, component swaps based purely on time intervals or maybe usage metrics like how many hours the machine has been running.
But it does matter what the actual condition of the asset is.
It doesn't matter at all. And while preventive maintenance does minimize some of those catastrophic failures, it leads to these systematic inefficiencies.
You mean waste?
A lot of waste. You often replace components that still have 20 or even 30% of their useful life remaining. It's called over-maintenance.
And that inflates costs, and I guess every time you open up a machine, you risk breaking something else.
You introduce the risk of human error, absolutely. And it's that inefficiency that really drove the industry toward data-driven strategies, which brings us to level 3.
Condition-based maintenance, or CBM.
Yes. And CBM is the crucial halfway house. This is where machines finally start talking to us through sensors.
So we're not using a calendar anymore. We're using real data.
We're using real-time data. You're monitoring key parameters, vibration, temperature, pressure. And if a sensor reading crosses some predetermined threshold...
Like a bearing gets too hot.
Exactly. Let's say a bearing temperature hits 180 degrees. That triggers a simple, rule-based alert. So now maintenance is scheduled based on the real-time condition of the machine, which is a huge improvement over just a cyclic schedule.
But CBM, it's still reacting to something that's already happening.
Right.
The bearing is already hot.
It's reactive to an existing condition, yes. The real prize, the big leap, is to level 4, predictive maintenance.
PDM. So how is that fundamentally different from CBM?
The difference is prediction versus reaction. PDM is powered by advanced machine learning models that are analyzing the rate of degradation, the operating context, everything,
To what exactly?
to accurately forecast the remaining useful lifetime, or RUL, of a component. So instead of getting an alert that the bearing is hot now, PDM tells you that based on the current data, that bearing has a 90% probability of failure within the next 45 days.
So you can plan, you can order the part, schedule the downtime for a slow period.
You replace the component precisely when it's needed, you maximize its lifespan, but you still avoid that costly, unplanned downtime.
And then there's one level above that. The pinnacle, level 5, is risk-based maintenance.
This is the strategic layer. This is where it gets really smart. Risk-based maintenance takes that highly accurate RUL prediction from your PDM system.
Okay.
And it combines it with a full operational and financial risk.
And that whole movement up the ladder into PDM and risk-based strategies, that's what's driving this incredible market acceleration.
It is. This isn't just a niche optimization anymore. It's the core economic engine of what we call smart manufacturing.
And the numbers in the source material really back that up.
They absolutely do. The sources confirm the smart manufacturing market is projected to hit just an astounding valuation of $1,097.26 billion by 2035.
Over $1 trillion.
With a sustained, robust 15.25% compound annual growth rate.
Yeah.
This isn't just, organic growth. This is a necessity. Companies that don't embrace this level of efficiency are going to really struggle to compete.
So what are the specific technologies really pushing this forward so quickly?
Well, the core drivers are all interconnected. First, you have the massive deployment of the industrial IoT, or IIoT. That's what finally connects all the machines, old and new, to the network to get the data stream.
So the sensors and the connectivity.
Right. Second, you have the rapid adoption of AI and machine learning, which is our focus today. Third, you have the expansion of advanced robotics and automation, because you need something to actually do the precise, high-speed work.
I see the robotics connection, but you also mentioned another key technology, digital twins. How do they fit into this?
Digital twins are essential for this kind of optimization. They are virtual, real-time replicas of physical assets.
A simulation of a real machine.
A perfect simulation. It ingests all the real sensor data, and it effectively mimics the asset's physical behavior in real time. So engineers can use the twin to test maintenance scenarios or model failure modes or run optimizations.
Without ever touching the real machine.
Without touching the real asset. It allows for zero-risk experimentation, which is just foundational to the efficiency that Industry 4.0 promises.
Let's bring the scale down to earth a bit with a concrete example. The sources mentioned General Motors.
Yes, a massive operation.
And their use of AI for maintenance is directly targeted at improving something called overall equipment effectiveness, or OEE. Can you define OEE for us?
Absolutely. OEE is the gold standard metric for measuring manufacturing productivity. It basically breaks down your total manufacturing time into time that is truly productive.
And how is it calculated?
It's calculated by multiplying 3 factors. You have availability, which is just uptime. You have performance, which is speed or throughput. And you have quality, which is the number of defects.
And a PDM system directly boosts at least 2 of those.
At least 2, yeah. It directly boosts availability by cutting down on unplanned stops, and it boosts quality by preventing the machine degradation that leads to defects.
So at GM, how does this actually look on the assembly line?
Well, GM is leveraging AI to analyze continuous data from thousands of sensors on their critical machinery.
What are they monitoring?
Things like subtle vibration patterns, transient space and temperature, minute variations in how much energy a motor is consuming. The sheer volume of this data is so huge that you need complex AI just to filter and process it.
And by predicting failures, they're boosting that availability score.
Significantly. Reducing unplanned downtime directly moves that OEE needle.
And it's not just about stopping a machine from, seizing up. It's also about quality.
Right. It's preventing a tiny flaw from being introduced into a component that might cost thousands of dollars.
So how are they doing that?
GM has implemented these AI-powered quality control systems, specifically using advanced computer vision.
Cameras on the line.
AI-powered cameras,
Yeah.
They're trained to spot tiny deviations or imperfections in real time as parts move down the line. And there was one documented success where these AI-based cameras detected 72 component failures on robot assembly lines
Before they cause a problem.
before those components could cause defects or, worse, a major operational failure. So it shows that AI's role really spans both the long-term mission health prediction and the immediate, real-time quality assurance.
Okay, so we've established the economic need and the high-level impact. Now we get into the technical battleground,
The messy part.
the messy part. And that means diving into the specific challenges of real-world industrial data. And for that, we turn to the bottling plant case study.
Yeah, this bottling plant scenario is just a perfect encapsulation of the typical challenges anyone in this field faces. The asset we're looking at is the input gripping pliers.
What do they do?
It's a rapidly rotating component that's crucial for handling and manipulating the bottles. It's under high stress, managing up to 9,600 bottles an hour.
Wow.
The mechanism rotates at 30 RPM, and it's handling 4 bottles with every single revolution. The vibration data is coming from a very sensitive piezoelectric accelerometer.
Okay, so we've got sensitive sensors, continuous, rich data on a critical moving part. What's the immediate, unavoidable roadblock that turns this rich data set into a major headache?
The immediate roadblock is the environment itself. The entire production line is designed not to fail,
Right, that's the goal.
which results in the absolute nightmare of highly imbalanced data sets. You're generating these vast, continuous streams of data, millions upon millions of data points that just represent healthy operation.
And almost none that represent a failure.
A tiny fraction, a vanishingly small number of data points that represent an actual failure event.
Can you put that imbalance into perspective for us?
I can. In this study, related analyses showed that the single most common type of failure resulted in only 228 starts per year.
228.
Right. Now, if your sensors are recording continuously, you could easily accumulate 8 or 10 million sensor readings in that same year.
So you're trying to find 228 needles in a haystack of 10 million pieces of straw.
That's it. And trying to train an algorithm to spot those 228 rare instances is almost impossible with standard techniques. The model will just learn to classify everything as healthy, because statistically, that's almost always the right answer.
And that problem is compounded by the sheer size of the raw signal data itself, right? Even for a short period.
That's the second layer of complexity, high dimensionality. The raw vibration signals are sampled at a very high frequency, 12.8 kilohertz, to capture all the nuance of the mechanics.
So if you take just a small slice of that data,
Even a relatively short segment, you are dealing with tens of thousands of features. In this specific case study, each segment, if you used it raw, generated up to 64,000 raw values.
64,000 features.
Yeah.
With only a few hundred failure examples, I remember the common wisdom in machine learning is that you need far more training examples than you have features.
It's an absolute rule. When you train a model directly on 64,000 features with such limited, imbalanced training data, you are 100% guaranteed to suffer from severe model overfitting.
Meaning it doesn't generalize.
It doesn't learn the general characteristics of a damaged bearing. It just memorizes the specific numerical quirks of those 228 failure segments you showed it. The moment that model sees a new, slightly different vibration signature in the real world, it fails completely.
So we have two core problems here. Too few failure examples and way too many redundant features. How do we start to tackle the limited sample size problem?
The first crucial step is a technique called data augmentation via segmentation.
Meaning we chop up the data.
We take that long, continuous signal stream and we just slice it into smaller, manageable, fixed-length windows. Each of those windows then effectively becomes a new labeled training example.
So you turn one long failure event into many smaller examples of that failure.
Zach, this dramatically increases our pool of training samples, even for those rare failure events.
But the length of that window can't just be random, can it? This seems like where the domain knowledge, the engineering expertise is critical.
This is the aha moment. This is what defines successful industrial data science. The window size has to be empirically determined to capture the complete mechanical context of the operation.
What happens if it's too short?
If the segment is too short, say half a second, it might only capture a fraction of the component's rotation. You lose the signature. The specific way the vibration spike repeats itself is lost. The segment just becomes meaningless noise.
And if it's too long, you're back to where you started, with not enough samples.
You negate the benefit of the segmentation. Exactly. So the empirical testing for these gripping pliers found that the optimal duration was a 5-second window.
5 seconds. Why 5 seconds?
Because at 30 RPM, the component completes 2.5 full rotations in 5 seconds. And that duration was found to reliably capture the full mechanical cycle, ensuring that all the necessary information about the fault was present in every single segment.
That's a brilliant example of where the data scientists and the mechanical engineers have to be in the same room.
It's the essential translation layer. You can't set that parameter without knowing the machine.
So once the data is segmented, we've got more samples. What's next?
The next strategy is to prepare the model for the messy reality of the factory floor. Because real industrial sensor data is inherently noisy.
Right. Interference, temperature changes.
Electromagnetic interference, temperature fluctuations, just random events. So instead of trying to perfectly clean the data, the strategy is to intentionally dirty it in a controlled way.
You add noise on purpose.
You add controlled Gaussian noise to the features. This noise had a mean of 0 and standard deviations of either 1 or 0.1.
And the purpose of that is what? To test the model's resilience.
Precisely. We are forcing the model to look past all the superficial details and learn the deep underlying structural patterns that persist even when the signal is degraded. This ensures that the successful classifiers are truly robust and don't just collapse the moment they see a real-world noisy sensor reading.
Okay, so we've solved the sample size problem through segmentation, but we're still dealing with this massive problem of 64,000 features per segment. We know that guarantees overfitting.
Right.
So now we enter this critical stage, feature engineering, where we have to somehow reduce those tens of thousands of data points into a handful of truly predictive signals.
And this is where we run into a core conflict in industrial data science. It's really a battle between traditional expert-driven signals and more generic data-driven statistics. We'll start with the expert-driven approach.
So these are features like kurtosis and root mean square, or RMS. These are the cornerstones of vibration analysis, right? Engineers have used these for decades.
For decades. They represent a vast amount of domain knowledge that's been codified into a calculation. Kurtosis, for example, is a statistical measure that quantifies the peakedness of the signal.
What does that mean, peakedness?
It's designed to spot the high-energy impulsive spikes that are characteristic of, say, a microfracture on a rolling element-bearing surface, a little crack. The root mean square just measures the overall energy level of the vibration. So together, they should theoretically tell you a lot about a bearing fault.
This sounds ideal. It's built on decades of engineering knowledge. Why would you need anything else?
Because the process to actually extract them is incredibly complex and computationally intensive, and it introduces multiple points where errors or noise can be amplified.
So you can't just calculate kurtosis from the raw signal.
No, not at all. It's a 4-step ritual. Step 1, you have to convert the raw time domain signal into the frequency domain using something like a fast Fourier transform, or FFT.
So that tells you which frequencies are vibrating.
Exactly. Then step 2, you use a specialized tool called the curtogram to find the optimal frequency range, the passband, where those fault-related impulsive events are most clearly visible.
Okay, hold on. The curtogram. For those of us who aren't vibration specialists, what is that actually doing?
It's a great question. Think of it like tuning an old analog radio. The machine is vibrating at many frequencies at once. The general hum of the structure, the rotation, the meshing of gears, all that is noise.
Right.
But a fault, like a tiny crack in a bearing, doesn't just increase the overall vibration. It creates a very specific, high-frequency, repeated tink noise. The curtogram scans the entire frequency spectrum and tells you exactly which frequency band contains the highest concentration of those sharp, repetitive energy spikes. It tells you exactly where to listen to find the fault.
Okay, so we've isolated the frequency band of the fault. What are steps 3 and 4?
Step 3, you calculate the signal envelope, often using a Hilbert transform. The envelope basically extracts the overall shape or outline of that rapidly fluctuating signal within your filtered frequency band.
So it's simplifying the signal.
It's extracting the timing and magnitude of the fault impulses. And then finally, step 4, you measure the kurtosis and RMS from that derived signal envelope.
Wow. 4 complex, specialized transformations just to get 2 numbers. What was the outcome when they applied these highly engineered features to the bottling plant data?
The results were genuinely shocking. While kurtosis did show the expected high spikes in specific faulty experiments, so it confirmed it can detect faults, the overall accuracy of the classifier built on these features was dismal.
How dismal?
We're talking about 34% accuracy. And more critically, When you did a 2D visualization plotting kurtosis against RMS, it showed poor separation between the different fault populations, like removed spring versus damaged bearing. They were all jumbled together.
Wait a minute, that makes no sense. If kurtosis and RMS are the gold standard for vibration analysis, custom designed for this environment, why do they perform so poorly? That feels like it contradicts decades of engineering wisdom.
That is the critical question this study answers, and there are a few key reasons.
Hmm?
First, these expert-driven features are often designed to find one very specific textbook failure, like a classic bearing fault. But in the real world, you might have combined faults or more nuanced failure types.
And the complexity of the process is a problem.
A huge problem. The complexity makes the feature highly sensitive to the exact operational conditions. It can amplify noise or environmental variability. And second, the computational cost is a massive factor. That entire four-step process takes about 0.24 seconds per segment,
A quarter of a second.
which doesn't sound like a lot, but when you need real-time prediction across hundreds of sensors, that latency adds up and it compromises the whole operational feasibility.
So too much specialization, too much computation, and too much sensitivity to noise, all leading to poor results with limited samples.
Precisely. And this brings us to the great alternative, the generalist approach, relying on basic statistical features.
This feels like a step backward. We're going from that complex four-step process to just, mean, median, and variance.
It is the elegant shortcut. Instead of trying to find the one perfect complex signal, we just derive a standardized broad set of generic statistical measures.
From both the time and frequency domains.
Yes, we extract features from the time domain, things like mean, median, range, variance, skewness, and yes, even the basic unprocessed kurtosis. And then from the frequency domain, we get things like spectral centroid, mean frequency, spectral spread, and spectral kurtosis.
And what's the immediate benefit?
The powerful benefit is we reduce the feature count from over 64,000 raw values to a manageable set of only 33 features.
33 features. And how did these sort of off-the-shelf statistics perform against those custom expert design features?
The comparison is a staggering endorsement of strategic simplicity. When both feature sets were compared using the exact same logistic regression model, the model trained on the basic features performed drastically better.
Bear.
For the crucial damaged bearing state detection, the basic features achieved a remarkable 95.65% accuracy,
95%.
compared to only 34.38% using the specialized kurtosis and RMS features.
That is an unbelievable difference. How could something so simple, so thoroughly beat years of specialized engineering knowledge?
Because the basic statistics, especially the ones from the frequency domain, they capture these macro changes in the signal's energy distribution over that whole 5-second window. They're less sensitive to the minute, localized noise that might corrupt a highly processed feature like the envelope kurtosis.
They're more robust.
They are. They effectively capture the mood or the overall shift in the machine's operation. And features like spectral kurtosis, which is the peakedness of the frequency distribution, not the time signal, proved particularly effective. It shows how energy is shifting across the frequency bands, which is often a reliable indicator of wear, but without all the computational cost of that full four-step process. Strategy, in this case, completely trumped complexity.
Okay, so we've successfully shrunk the feature space from 64,000 raw signals down to 33 robust basic statistical features. That was the primary breakthrough.
A huge one.
Now we move into the refinement stage, where we find the most efficient representation of even those 33 features.
And this is where a technique called principal component analysis, or PCA, comes in. Now, PCA is not feature selection. It's dimensionality reduction.
What's the difference?
It mathematically transforms the existing correlated features into a smaller set of new independent composite variables. We call them principal components. And it does this in a way that preserves the maximum amount of variance or explanatory power in the data.
So how efficient was PCA at compressing the information that was in those 33 basic features?
The efficiency was extraordinary. It really demonstrated how organized the underlying physical data actually was once you looked at it the right way. For those 33 basic features, only 4 principal components were needed to account for 92.17% of the total variance in the data.
4 numbers explain 92% of everything.
And if you wanted almost complete representation, just 9 components accounted for 99% of the variance.
So you could explain virtually everything about the machine's health using only a handful of composite numbers rather than 33 individual statistics. That is compression on an industrial scale.
It simplifies the training process immensely. It's the ultimate proof of that strategy over scale thesis. And what's more, when PCA was applied to the original raw data set,
Before the 33 features were even extracted.
yes, it performed so well that simple classifiers like a logistic regression or a support vector machine achieved perfect cross-validation scores.
100% accuracy.
100% accuracy with as few as two principal components.
That's incredible. 100% accuracy using two numbers derived from 64,000 raw values. What does that imply?
It implies that once the data was normalized and the relevant underlying information was extracted into those principal components, the actual classification problem, is the bearing healthy or is it damaged, became remarkably trivial for the AI to solve.
It exposes this hidden simplicity in what looked like a chaotic, high-dimensional problem.
It really does. And PCA also proved its robustness. When the researchers tested it with high levels of that Gaussian noise added, it still performed excellently. You needed a few more components to get the same high accuracy, but the total number was still drastically low. PCA acts as a powerful noise filter and a compression tool. It's indispensable.
Okay, so moving from that kind of projection to actual selection, we still want to know which of our original 33 features were the most important predictors. The mathematically purer way to do that would be exhaustive search.
Right, testing every single possible combination of features.
But as you hinted at earlier, this is where computation just slams into a brick wall.
The computational infeasibility of exhaustive search is the starkest warning against brute force in data science. With 33 features, testing every possible subset is mathematically defined by the power set.
And that means?
That results in over 8.5 billion combinations to test.
8.5 billion.
And even if you fixed the model hyperparameters and make some very optimistic assumptions about computation speed, the estimated time for an exhaustive search ranged from 1.72 years for a simple logistic regression model,
Over a year and a half.
up to an astronomical 157.32 years for a neural network.
157 years. That's not a business decision. That's a mathematical wall. We literally cannot brute force this optimization problem.
Which means strategic shortcuts are the only way forward. You absolutely must rely on practical feature selection techniques. And they fall broadly into two camps: wrapper methods and filter methods.
Okay, let's start with the wrapper methods.
So wrapper methods interact directly with the classifier. They train and test the model over and over again using different subsets of features to see which combination gives the highest predictive accuracy.
What are some examples?
The key examples here are recursive feature addition, or RFA, and recursive feature elimination, RFE. RFA starts with 0 features and iteratively adds the one feature that gives the biggest boost in model accuracy.
And RFE is the opposite.
It does the opposite, yeah. It starts with all 33 features and then removes the least important one at a time. And in the study, RFA proved to be highly efficient. It consistently showed the highest accuracy gain with the fewest number of features.
And then we have filter methods. How are they different?
Filter methods use statistical measures that are independent of the classifier. You have the standard correlations like Pearson and Spearman, but the most powerful tool here is the one that can handle the messy, nonlinear reality of a factory floor.
And that is?
That is the crucial measure of mutual information, often implemented using something called the Linfoot measure.
So standard linear correlation Pearson, it only captures straight line relationships.
Right. And monotonic correlation, Spearman, captures relationships that always go up or always go down, even if they aren't in a straight line. But industrial processes are often way more complex.
They're not linear.
They're not linear and they're not monotonic. Imagine a feature relationship that looks like a sharp V shape or a quadratic curve. Standard correlation metrics would look at that and say there's no relationship. They'd miss it completely.
So what does mutual information look for?
Mutual information is relationship agnostic. It captures any form of dependency between a feature and the target state. It quantifies how much knowing the value of feature X reduces your uncertainty about the health state, Y.
So it can spot that V-shape.
It can spot the V-shape, a sine wave correlation, any complex nonlinear dependency that often defines those subtle mechanical failure modes. This makes it highly generalizable and really a non-negotiable tool for feature selection in these complex frameworks.
So using all these tools, RFA, RFE, mutual information, which of the 33 features consistently rose to the top as being most important?
There was a remarkably strong consensus across the board. The most important features, almost every time, were strongly related to the frequency domain.
Specifically?
Specifically, features like spectral kurtosis, F8, mean frequency, F2, and spectral spread, F5, were repeatedly ranked as the top performers.
Which just solidifies that earlier finding.
It completely solidifies it. The critical predictive power lies in the frequency spectrum, and simple statistical measures derived from that spectrum, like how peaked it is, where its energy is centered, and how spread out that energy is, those are the key identifiers of an imminent failure.
We've focused so heavily on the bottling plant to illustrate this technical deep dive, but the lesson segmentation, basic statistics, strategic feature selection, they apply universally.
Absolutely.
So let's shift now to two other very demanding, high-stakes industries, wind turbine operations and healthcare.
Yeah, and wind energy provides a great contrast. A failure in a massive offshore wind turbine isn't just an operational cost. It's a huge logistical challenge and a massive loss of revenue.
So the PDM frameworks here, they mentioned GreenGuard and CMS-ML. They have to manage multiple disparate data streams at the same time.
They do. Let's look at those data streams. You have two major types coming from a modern wind turbine. First, there's the high-frequency signal data, which is handled by the CMS-ML framework.
The Condition Monitoring System Machine Learning Framework.
Right. And this involves extremely detailed, high-temporal resolution vibration data. We're talking FFT spectrums, raw t-values, offset, and delta values. It's used to diagnose the state of rotating parts like the main bearings and the complex gearboxes.
So this is the data that requires that complex feature engineering we were just talking about.
Exactly. This is where you're transforming the raw signal into RMS, kurtosis, skew, and so on. But the second, and equally vital stream, is the operational context data.
Where does that come from?
That's often pulled from SCADA systems and work order logs. SCADA provides aggregate low-frequency data, usually collected every 10 minutes.
So things like wind speed and power output.
Average power output, wind speed, the pitch angle of the blades, turbine temperature profiles, very slow contextual data.
So you have very slow contextual data from SCADA and very fast diagnostic data from CMS. How does the GreenGuard framework use the human element to bridge that gap and create useful machine learning targets?
GreenGuard is essentially a prediction engineering library. It's designed to turn the messy reality of operational log stoppages, human work orders, text notifications into codified targets for the AI. It does this using labeling functions.
Labeling functions.
Yes, and they're defined by subject matter experts. So imagine an experienced engineer knows that certain keywords in a maintenance tech's repair log are highly indicative of a precursor event to a bigger failure.
Okay.
That expert uses GreenGuard to define a specific label, for instance, a yaw system stress incident. The labeling function then automatically searches all the unstructured text fields for combinations of keywords like yaw and repair and abnormal noise.
And when it finds them?
It then assigns a time window before that event as a failure precursor sample for the model to train on.
That's fascinating. So you're codifying the intuition of an experienced engineer. The human doesn't have to sit there and manually label thousands of hours of data.
No, they just define the rule once, and GreenGuard rapidly generates the targets for the AI model. It's an iterative, flexible approach that ensures the ML solution stays constantly relevant to what the field engineers are actually seeing.
Now let's pivot to that final application, the one where the stakes are arguably the highest, PDM and healthcare.
Yeah.
Here, failure means patient risk, not just a financial loss.
It's a completely different level of risk. The application of AI-driven PDM to critical medical equipment monitors, ventilators, imaging devices is all about continuous surveillance of structured sensor data like temperature, pressure, and flame rate.
But the challenge seems immense because the frameworks have to be so human-centered.
Deeply human-centered. You're not just involving technicians and biomedical engineers. You have to consider the impact on clinical staff, on patient workflow. It has to be perfectly integrated.
And the data complexity must be unique here too. You're not just dealing with machine vibration.
No, the diversity of data sources is the primary hurdle. The systems have to integrate the standard structured sensor data, but also highly valuable, often chaotic, unstructured data.
Right, what?
We're talking about technician maintenance records, which are often just free-form text notes. You also need to integrate the fault codes the equipment generates and even potentially images of faulty components that a technician takes with their phone in the field.
That unstructured data provides the context.
The rich contextual layer that's necessary to truly understand why something failed.
And the regulatory and operational environment is so much stricter than a factory floor.
Oh, absolutely. Operationally, hospitals have these diverse, often proprietary IT systems for everything. The PDM PDM solution has to seamlessly integrate across this entire infrastructure, which often requires robust, specialized middleware solutions just to translate and move data between these
And
systems.
then there's privacy.
Right. Unlike a factory, these systems have to strictly comply with regulations like HIPAA or GDPR. That means end-to-end encryption and a highly secure cloud storage to protect patient confidentiality. The integration challenge is technical, logistical, and ethical all at once.
So that core lesson we pulled from the bottling plant, that data strategy has to triumph over data volume. It's just amplified in healthcare, where the cost of a failed prediction is measured in patient safety, not dollars. This deep dive has, it's traveled from the high-level economics of the trillion-dollar smart manufacturing market all the way down to the granular mathematics of data compression.
It's been quite a journey.
We established that critical leap from just condition-based maintenance to full predictive maintenance, and it's all driven by the need to predict that remaining useful lifetime with precision.
And we found the most important lesson through that industrial case study. The bottleneck in PDM isn't data collection, it's managing the complexity that comes with it.
Wow.
We proved that bypassing that costly, complex, specialized feature extraction like the four-step kurtosis process in favor of simple, standardized, basic statistical features drastically improved predictive accuracy.
By nearly 60 percentage points.
Yeah,
It was a staggering difference.
it was.
And then the refinement stage is just pure genius. We saw the raw, transformative power of principal component analysis, or PCA.
Which, by preserving over 92% of the data's variance in only 4 components, allowed simple classifiers to achieve 100% accuracy.
And we learned that the 157-year computational cost of trying to brute force feature selection is avoided through these highly strategic targeted methods.
Methods like recursive feature addition and that relationship-agnostic mutual information.
So the synthesized takeaway for any engineer or strategist listening is what?
It's singular. The feature engineering step is your most powerful lever. The difference between failure and success in industrial AI hinges entirely on your ability to reduce dimensionality without losing explanatory power. The most powerful solutions come from transforming that chaotic, high-frequency noise into potent, low-dimensional statistical signals.
With those frequency domain characteristics like spectral kurtosis and mean frequency proving to be the consistent stars.
Consistent stars across all kinds of different machines.
So what does this all mean for you, the learner? Well, the greatest competitive advantage in this burgeoning world of Industry 4.0 is not having the largest data lake, but mastering these strategic shortcuts.
Absolutely. Knowing that inexpensive techniques like recursive feature addition or using a generalized measure like mutual information can save you years of computational time while delivering superior, more robust results, that is the knowledge that translates directly into a competitive advantage.
And this leaves us with a final provocative thought.
If complex, nonlinear relationships and highly specific machine data streams data representing physical forces, movement, and heat can be accurately characterized by simple statistical aggregates like mean frequency and spectral kurtosis, what powerful unseen patterns are currently hiding, unextracted, and waiting to be revealed in the equally complex, high-dimensional data streams flowing through your daily life?